Ready? On your mark, get set. Here we go, here we go, here we go. Today, you learned something that you're going to use for the rest of your math career. We're going to learn about parent functions and how to transform them and put them in, or translate them, put them in different positions. So, linear functions such as y is equal to a constant. Horizontal line. Just change a constant, changes the location. You're most familiar with y is equal to x. That's the parent function for linear functions. We spent a lot of time doing y is equal to mx plus b, where you change the slope of the y-intercept, it changes its location and everything else. Absolute value function is like a linear function because it's to the first degree. But I want to make sure that everybody understands why the graph has the shape that it does. What? If you take the absolute value of a negative, you get a. So notice how it's going to look the same as this function. It's just going to have this piece reflected up into the portion above the x-axis. So that's why you get the shape that you do. We're not going to talk about the greatest integer function. It's really not that important. Power functions. You know some of these. Y is equal to x squared. You know the parabola looks like this. Y is the graph of y equals x squared. Why is it always above the x-axis? Because if you square something, it makes it positive. So if you cube something here, you're always going to get a positive. So therefore, you're going to have portions that sit below the x-axis. We have something like y is equal to x to the fourth. Looks very similar to y is equal to x squared. But it gets a little bit more vertical along the sides and a little bit flatter along the x-axis. Kind of like y is equal to x to the fifth. Again, a little steeper on the sides and flat along the x-axis. Okay. Yep, they're testing my patience right now. All right. So I turn this on, and what I'm going to do is I'm going to show you something kind of cool. Look at y is equal to x squared. And then what I'm going to do is I'm going to show you what happens if we increase the degree. So I'm going to go x to the 8th, and I'm going to go x to the 100th power. So watch what happens if we increase the degree. Window, I'm going to take it to -2 and 2. I'm going to graph this guy. Watch x squared. Here's x to the 8th. Watch x to the 100th. Oh, see that? And here's why that happens. Because if you take 1 and raise it to the 100th power, what are you going to get? 1. But if you take a number just to the side of 1, say 1.1, and you raise that to the 100th power, you can see you get a ridiculously large number all of a sudden. Whereas if you go just to the other side of 1, let's say you take 0.9 and raise that to the 100th power, you get an extremely small number, which is why the graph has the shape it does. It stays small all the way until it gets to 1, then jumps up to 1, and then after 1, it jumps way up. So again, I want you to understand why the graphs have the shapes that they do. Root functions. So suppose we have y is equal to the square root of x. You guys know that one, but we haven't talked about y is equal to the cube root of x. So y is equal to the cube root of x. You can see in that situation, can you take the cube root of negatives? So it's going to produce negative values for negatives and positive values for positives. So you can see it's located both on the right side and on the left side. If we have a fourth root, y is equal to fourth root of x. It looks very similar to the square root because you can't take the fourth root of a negative. But y is equal to fifth root of x. Do you think that's going to look more like the square root or the cubed root? The cubed root. You need to have these functions committed to memory. If you just think about why they have the shapes that they do, it's not that difficult. These are a little bit more challenging. Other root functions, such as y is equal to x to the 2/3, or y is equal to the cubed root of x squared. Let's think about why that one would have the shape that it does. If I plug in a positive and you square a positive, you get a positive, right? And then you cube root a positive, you still come up with a positive. What happens if I plug in a negative? Can I square a negative? Yeah, you get a positive. So would you agree that no matter what I plug in, it always comes out positive? And so therefore, you get this kind of shape. I call it the bird function. Because if you want me to draw a picture, you say draw a person, that's how I draw a person. You want me to draw a bird? Draw a bird. Okay. All right, somebody's laughing. You want to show me up? That's how you draw it too? I didn't know if you want to come up and show me your artistry and everything. Okay. Jack, you making fun of me? Okay, Jack, you want me to show it? Come up here and draw a bird? Raise your hand if you like Jack to come up and draw a bird. All right, come on up, Jack. Here he goes. Jack is going to show us the artistic talent. Oh, wow. Okay. All right, that's the bird, I guess. Anybody else? What, you think Jack's bird is better than mine? Some people, you can't wait till they graduate. Oh my gosh. All right, here we go. So what happens if we go y is equal to x to the 3/2? Well, that's interesting because now in this situation we have y is equal to the square root of x cubed. Now I want you to notice here, you plug in a positive, you're going to get a positive, right? But how about a negative? You cube a negative, you get a negative. Can you take square root of a negative? So you can't actually plug in any negatives. It's like y is equal to x to the 1.5. You might think of it. It's between 1 and 2, but you can't get any negatives. So you kind of get just half of a parabola almost. It's just not as steep as a parabola. Reciprocal functions, you're going to see those a lot. Y is equal to 1 over x. Now, who can tell me what value can you not plug in for x? Y. So you can't divide by 0. Very good. So you have this thing called a vertical asymptote. Can you say asymptote with me? Ready? 1, 2, 3. Asymptote. Now, the first time I said asymptote in class, people started laughing at me. And I said, "You stupid Mr. Gaines. It's not asymptote. It's asymptote." Actually, I hate to invoke that I'm right. I took 4 semesters of Greek. It is a Greek word. You're allowed to pronounce it 2 ways, asymptote or asymptote. I don't like to say asymptote. It looks like I'm putting the emphasis on asymptote or like but. We don't like to talk about but, do we? So if you want to say asymptote, that's fine. It's free country, freedom of speech, First Amendment, right? Yeah, most time. So, gets a bomb in an airplane. All right, so, well, I mean, now, So an asymptote is an imaginary line the graph approaches but never actually touches as it heads out to large values. So, and I also have a horizontal asymptote in this situation, which is really interesting because, well, we'll just try it out here, okay? So watch what happens here. William, give me a number. So he gives me 5. If I plug in 5, I get a fifth. Give me another number, Jack. If I plug in 14, I get 1/14. Cool. Somebody give me some number that's a little bit more interesting. Okay, how about a third? What's 1 divided by a third? 3. See how it flips it? You plug something in, and you get the reciprocal value. That's why I call it the reciprocal function. You plug in small numbers, they give you big numbers. Plug in big numbers, they give you small numbers. Plug in 1, and you get, because the reciprocal of 1 is 1, isn't it a beautiful thing? What number could you plug in to produce 0? What number could you plug in here so that y would be 0? Nothing. That's why you have a horizontal asymptote through 0. You can't ever get 0 out. The graph looks like this. Small numbers produce big values, big numbers produce small values. Easy, simple. Y is equal to 1 over x squared. How is that going to change the graph? You know this. You're smart. I like your idea of parabola. Think positive, negative. No negatives, right? So you're going to have the same kind of graph. It just always sits above the x-axis. Cool. Lots of cool functions, right? I mean, just think, this is like a little family of functions that you can check out. There's functions that you have no idea what they look like. I'm going to show you my favorite function of all time. All right, YouTube, we just kind of digressed. We looked at the barcode function, which obviously is super fun. And so now, what are we going to do with these? We're going to transform them. We're going to move them around. So we're going to do the second page. The equation, say we have f of x. Well, I'm sorry. Y is equal to f of x plus k. So we're going to take a function and we're going to add k. And notice how we're going to add it to the outside, or f of x minus k. And this is the most important thing that you can learn from chapter 2, is that when something happens to the outside, it affects it vertically. That will save you points on the test. When something happens outside, it affects it vertically. This goes up k units. This goes down k units. But when you have something on the inside, it affects it horizontally. So y is equal to g of x minus h, or y is equal to g of x plus h. When you have something on the inside, it has a horizontal impact. H units right, H units left. Now you remember some of this from previous years. Notice how that the minus is right and the plus is left. So you should be able to identify the parent function and then be able to sketch the graph. So I just want to be clear, folks. We've done a lot of different things where you make like X and Y charts. You remember doing that before, right? And you remember finding X and Y intercepts. And intercepts, those are really cool too, right? Well, here's a new way of graphing stuff, and it's by far the fastest. You simply look for the parent function. In this case, it's going to be x squared. And then you think about the transformation. Is the minus 3 on the inside or outside? Outside. So that could be vertical or horizontal. Vertical. So it's going to shift it down 3 units. Look how easy that is. Square root of x minus 4. We know the square root function. It looks like that. Is the minus 4 on the inside or outside? It's on the inside. So it's going to move it 4 units to the right. Carson made a very good point here. And I want to be clear. Look at this, folks. If you ever decide to move it 4 units to the left, so you plug in -4, you're saying it would go through the point -4 is 0, correct? Watch what happens. -4 minus 4 gives you -8. Square root of -8 is not 0. But if you move it to the right, that means your x value is 4. And your y value should be 0. Well, 4 minus 4 is 0, and the square root is 0. See how you can check your answer? You can plug in the point and make sure that it goes to where you wanted it to. The next one, you know what the cube function looks like. It looks like that. What's going to happen to this one? Down 2, left 3. Left 3, down 2, bada bing, bada booski. Square, absolute value function. I know that guy. Looks like a V. What's the transformation? Right 4, down 3. Right 4, down 3. Oh, I put it upside down. I ate a bowl of stupid for breakfast. Okay, last section then. What about a vertical reflection? It's going to be on the outside. What about horizontal reflection? It's going to be on the inside. It's on the outside, it's vertical. So y is equal to negative f of x. Or y is equal to g of negative x. You can see the difference between the outside and the inside. If you see the negative on the outside, it's a vertical flip. And if it's a vertical flip, is that going to be over the x-axis or y-axis? X-axis. Negatives on the inside, horizontal flip. Over y-axis. Now here's where I'm going to kind of cheat. You two, I apologize for this, but I'll try to explain what I'm going to do here. I'm going to show you different ways in which we look at these flips. The horizontal flip tends to cause some issues for people. We're going to show you when it's really important to think about when it's not, okay? It says identify the parent function of the following, graph the new function, describe the transformation. Well, you know that the square root of x looks like this. Is it negative on the inside or outside? So is that going to be a vertical flip or horizontal flip? Vertical flip. Any questions about that? So the question is, what if you had this, the square root of negative x? Well, now the negative's on the inside, isn't it? And so therefore, your graph is going to go back to this side. Suppose you had negative square root of negative x. Well, now it's both a horizontal and a vertical flip, isn't it? This one is where you need to be really concerned about the horizontal flip. There's really no other functions where you need to be concerned about the horizontal flip. And I'll show you why. When you look at this one, you like to say, oh, I see a positive 3, so it's going to move it left 3. And I see a negative x, so it's going to make a horizontal flip. Don't think of it like that. Think of it as this is a parabola, right? Just think about what would happen if you multiplied it out. 3 minus x squared, isn't that x squared minus 6x plus 9? Aren't those the same? And isn't that the same as just x minus 3 squared? It turns out these are the same. They're different by a factor of -1, but when you square a -1, they become the same. So here's how I try to think of it. When you square this out, is it going to be a positive x squared or a negative x squared? Positive x squared, correct? So it's going to go up. Then what would you plug in to make 0? What would you plug in to make 0? 3. So it moves it right 3. What would you plug in to make 0? 1. So it's going to move right 1. It's going to move it up 4 and a vertical flip. So you know what the cubed function looks like. Looks like that. And then we see that you have right 1, up 4, and a vertical flip. What would you plug in to make 0? 5. So it moves it right 5. Negative on the outside creates a vertical flip. The only time you really need to worry about a horizontal flip is if you have the square root of a negative. Now, I say that, and I almost want to apologize mathematically because we would never write that in a textbook. But in practicality, that's really how it works out, is when you have that radical piece. Okay.